Okay. Good morning, friends, and welcome back to the second hour of this lecture. Before the break, we looked at the first two laws of black body radiation, which is Planck's law and Wien's law. Okay. Now what we are going to talk about is the third law, which is the Stefan-Boltzmann law, which, as we said before, gives us an expression to calculate the emissive power, the total hemispherical emissive power, or in short, the emissive power of a black surface. Okay. The Stefan-Boltzmann law or SB law. Now, again, let us draw our good friend. And what did we say? How is the emissive power and monochromatic emissive power related? One is the integral of the other, or the other is the derivative of the second is the derivative of the first. Did I say first and second correctly? You understand what I'm trying to say, okay? Okay, so this was EB lambda as a function of lambda, and so this area under the curve, right? So EB is integral 0 to infinity EB lambda d lambda. Now we have an expression for EB lambda, okay, from Planck's law. So I can do that. I can write 2 pi C1 is a constant. I can take it outside the bracket. 0 to infinity d lambda divided by lambda to the power 5 e to the power C2 by lambda t minus 1. Okay. So now you can go through a derivation, put x equal to 1 by lambda. Okay, therefore dx equal to minus 1 over lambda squared d lambda, blah, 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 all that stuff. And you come over here, and finally what you get is EB is 2 pi C1 0 to infinity x cubed e to the power C2 x by t, okay, because x is 1 over lambda, minus 1 to the power minus 1 dx. Okay, if you do all these substitutions, you will get this. Now what is this? This is e to the power 1 over e to the power mx minus 1. So which we know can be expanded. You know that probably even better than me. So if we expand the exponential series and integrate term by term. I hope these are, yeah, I think these are correct English, right? Term-wise integration, okay. What do we get? EB is going to be 2 pi C1 6 t to the power 4 divided by C2 to the power 4 1 plus okay. Now it's some of the things we know for a given temperature. what is going to be C1, C2 are constants, we know that. So everything outside the bracket we know. Inside the bracket also, it's a series, infinite series with decreasing terms. Okay, so it can be shown that this 1 plus 1 over 2 to the power 4 plus 1 over 3 to the power 4 plus blah 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 going to infinity is actually pi to the power 4 by 90. Okay, so what is it? Therefore, EB is a bunch of constants times t to the power 4. Okay, so EB is therefore that constant, that bunch of constants I'm talking about is our good friend sigma, which you know already is called the Stefan-Boltzmann constant or SP constant, and there's a value of 5.67 into 10 to the power minus 8 watts per meter squared Kelvin to the power 4. Okay. We know this. We have all seen this before. This is our good old friend, Stefan-Boltzmann law. So far we took it at face value. Okay, this is what the law, this is a law, okay, we have to abide by it. But what we have seen is that it has been derived. It can be derived starting from Planck's law and the basic definitions of what is monochromatic emissive power and what is emissive power. Okay. Now, friends, please note what we have done. It looks easy. Okay, what we have done is we have derived Stefan-Boltzmann law from Planck's law. Right? That's what we have done. We started with Planck's law and derived Stefan-Boltzmann law. And it looks easy. And you may be wondering that, well, what was the big deal? I mean, somebody already did something, you just did an integration based on the definition and you have a law in your name. Right? We have solved such problems in JEE. The truth is, Stefan-Boltzmann law came about 50 years before Planck's law. Or rather, Planck's law came 50 years after Stefan-Boltzmann law. So Stefan and Boltzmann didn't have the luxury of knowing Planck's law. Now we can, once we know Planck's law, we can derive Stefan-Boltzmann from there. But actually, when Stefan-Boltzmann law was first presented, it was before Planck's law. Any questions? So this brings us to the end of the laws of blackbody radiation. Planck's law, Wien's law, Stefan-Boltzmann law. The three pillars on which emission characteristics or blackbody radiation stands. Now let us say if I ask you that, yes, I can get the total emissive power using Planck's law. Okay, and even Stefan-Boltzmann law, which has already been done. But what if I want radiation over a certain range of lambda? What will you do? Okay, so the question that I'm posing, what if we want to calculate radiation, and radiation as in thermal radiation, or the emissive power over range of lambda. Somebody asked me, no, I just want it till here. So which means I need to calculate this area. Okay. So how do I do this? So yeah, it is obvious that it's not a big deal. If I want EB from 0 to lambda, I'll have to do 0 to lambda, EB lambda d lambda, 0 to lambda naught, let us say. Okay, so what I'm trying to say is the upper limit of this integration is changed from infinity to lambda naught. Okay, and dB lambda is given by Planck's law. Okay, so it is possible. But what has been done is some of our predecessors, they have made this task easier for us. So we can do this. I mean, it's not wrong. What I've written here is not wrong. But instead, what we do is we have these terms. Okay. So these are some of the, I mean, I am denoting it by D. I mean, in some books, it may be something different. D0 lambda is given by radiant flux emitted over 0 to lambda divided by emitted over 0 to infinity. Okay. So what does it essentially mean? It means that this expression is actually 0 to lambda 2 pi c1 lambda to the power 5 e to the power c2 by lambda t minus 1 times what is radiant flux emitted over 0 to infinity? The Stefan Boltzmann law. So 1 over sigma t to the power 4 d lambda. Okay. So now you change the variable from lambda to lambda t. Okay, because you have, the reason is you have lambda to the power 5 t to the power 4. Okay. Then you have lambda t. Okay. So what is d lambda? D of lambda t is t times d lambda. So this essentially becomes simpler. So I can write d 0 to lambda is equal to 0 to lambda t 2 pi c1 divided by sigma lambda t to the power 5. Okay, because we had lambda to the power 5, we had t to the power 4, so we need an additional t. We will see what to do. What is d of lambda t? T d lambda. Okay, So that T comes up, and that is how I could get the additional temperature in the denominator. Okay.
So, sir, will that be lambda square T in the exponent?
Huh?
In the exponent, will that be a lambda square T?
Lambda square Ty. It is C2.
Wait, okay, we are not replacing this in the way.
Huh? I'm sorry.
Never mind, sir. I got it. Never mind.
Got it? Okay.
Yeah.
Yeah, the whole the whole reason why we did this substitution is because in Planck's law you have lambda T. That's all. Okay. So this now gives us a combination parameter lambda T. This is integrable. People have done that numerically. Okay. So people have integrated the above numerically, and we have now and given a table like this. Okay, any standard textbook will have this. Okay, so I will give you some representative values. Let us say 600 micro Kelvin or micron Kelvin, 800, 1000, 4000, sorry, 10,000, 50,000. So if I have to write some values, this is going to be very, very low, 0.000000001 maybe. Next one 0.00002. At 1000, 0.00032. So the numbers keep increasing. At 4000 it becomes 0.48088. Okay. 0.91420. 0.998895 actually. Okay, so this is how you see that as this number keeps increasing from 600 to 50,000, the value has changed from almost 0 to almost 9. Okay, so if I now plot these values, if I write d0 lambda, of course it can never exceed 1. And this is lambda t. The nature of the curve is something like this. Starts, yeah, at 0 it is 0, definitely. Okay, so this gives you how much is the amount of radiation over a certain range of wavelength starting from 0. Right? So you can just go into this lookup table. You calculate what is the total emissive power, which is sigma t to the power 4, and multiply this by this fraction d0 to lambda for that lambda t, and you get it. Okay, so what are the steps? 1, calculate lambda t. 2, find d0 lambda for that lambda t. From the above table. and calculate EB 0 to lambda as D0 lambda times EB, where EB is sigma T to the power 4. Okay. Corollary. What if you have to calculate EB lambda 1 to lambda 2 so the starting point is not 0, starting point is lambda 1 in this range, let us say 50 microns to 500 microns. What is the black body radiation? Radiant flux, black surface radiant flux. How will you calculate?
Sir, we can
Take
use
into
apply.
lambda 2.
Exactly, very nice. Yep. So what you will do is this is going to be EB 0 lambda 2 minus EB 0 to lambda 1. Okay, which essentially means D0 lambda 2 minus D0 lambda 1 times sigma T to the power 4. Okay. Excellent. So let us take up a problem. Very simple one. The problem is calculate the maximum value of monochromatic emissive power. So just 1 minute, huh? You also? Calculate the maximum value of the monochromatic emissive power of the radiation emitted from the surface of the sun. Okay, assume temperature of sun's surface is 5779 Kelvin. Actually, I should not have written this. I should have written E lambda. And the surface to be black. Okay. So what does it mean? It means that since surface is black, E lambda is equal to EB lambda. Okay. So the question is, what is EB lambda max? How will you do it?
We can find lambda using Green's law, then we use Planck's law.
Excellent. Absolutely. Wonderful. So I will just write down the steps. You can work out the calculations later. Use Wien's law to get lambda m. Use Planck's law to get EB lambda at lambda m. Okay. The answers as per my calculations will be answer. Lambda m will be 0.502 microns and EB lambda max is 8.303 into 10 to the power 7 watts per meter squared microns. Okay. Achha. So let me expand this problem now and tell you that what is the value of the radiation when it reaches the earth. Okay. So part B of that problem. Okay, so I need to give you some data. Distance between Sun and Earth is 1.5 10 to the power 8 kilometers. And radius of the Sun is 6.95 into 10 to the power 5 kilometers. Okay, 3 orders of magnitude low. Okay, so in other words, what is happening is you have the Sun here. And it's of course radiating in all directions. And somewhere here you have the Earth. And this radiation is going to, come and fall on the Earth's surface. So this is, what do you think, what will happen? So at the Sun's surface, we can find out what is the emissive power, either the total emissive power or the monochromatic emissive power. Now the question is, what fraction of that is going to reach the Earth's surface? How will you find that out?
We can probably total just the sphere of radius r in r.
Again, come again. I think let me increase the volume a bit. Yes, please.
Sir, I'm saying that first we can probably find the total the gradient power using the sphere of radius r. Then we can use a sphere of radius r plus d.
Okay. So then what would happen? So how would it vary? How would it vary as a function of that radius?
So it will be r cube divided by r plus d cube. Oh, sorry, square. R square divided by R plus D square.
Exactly, correct. Not R cubed, R squared. Yes, absolutely. So, what Mr. Sodhi said is absolutely correct. The flux is going to vary as 1 over R squared. Why? Because the surface area of a sphere surface area is 4 pi R squared. Okay, so therefore EB lambda at Earth as in Earth surface is equal to EB lambda sun times R sun squared divided by whether it's R plus D. That's a good point you have raised. The problem stays distance between sun and earth. Now, is it center to center distance or is it surface to surface distance? We don't know. But probably since one is 3 orders of magnitude higher than the other, it doesn't matter much. So I would put it as distance squared. Okay. You can put R plus distance squared also, R sun plus distance squared also. What will happen is it will make some, it will be 6 point for the 1.5 plus 10 to the power 8 here, though 0.00695. Okay, so probably very little. 0.1% difference is what you're going to get. So I'm taking distance. Okay. So after that, it's fine. Similarly, EB at Earth will be EB of sun times again R sun squared divided by distance squared. Okay. So the sun's temperature was given to you. So sigma T sun to the power 4 times okay. So this turns out to be 1365 watt per meter squared. Okay, if you do this and assume the sun to be whatever the value I gave, what was it? 5779, 5780 Kelvin. This is what you're going to get. So this many a times, and people who work in solar energy, this is something of, this parameter is of great consequence to them. So this is called the solar constant. So this kind of gives you an idea that over 1 meter, I mean, the amount of solar energy, maximum amount of solar energy that can fall on a 1 meter square. What is 1 meter square? That's nothing, right? It's like 3 feet by 3 feet. 1 meter by 1 meter, slightly more, is 1.36 kilowatts. Okay. Think about it. Most of our household appliances which can run on the 5 ampere plug is less than 1 kilowatt. Okay. So if I am able to capture the sun's energy over a 1 meter squared, I can 1 meter squared, okay, which is a small amount. I can run most of my household items. Forget fans and lights, which are very small. Okay, which are, I mean, these LED lights today are single digit, right? Or maybe at most low double digit watts. True. But of course, you don't get this because, firstly, as it comes through the atmosphere, remember we said that for this course, we are not going to assume the role of the participating medium. This is what will reach the Earth's surface if it's vacuum. But of course, if it's coming through different layers of the atmosphere, and of course, in big cities, it's polluted air. So a lot of it is going to get attenuated. Then if it's a cloudy day, yeah, the cloud is going to absorb, you're not going to get this, so on. So all that has to be kept in mind, but this is theoretical maximum that you can get. So that's solar constant, okay? And after that, it depends on your solar panel. I mean, how efficient is it? How much of it can be converted to electricity, okay? Whether it's solar photovoltaic or you're using it as a solar thermal power plant, whatever it is, okay, the sun's energy, how efficiently can I use? Okay, if you calculate EB, which is the emissive power of the sun, assuming that temperature to be 5779 Kelvin, you are going to get something in the order of 10 to the power 7 watt per meter squared. Okay. But as you can see, it gets attenuated quite a bit because of this distance. All right, so that's the problem. And through this problem, I wanted to also talk a bit about solar energy. Let's do another problem. (9:39). Yes, I think we should be able to complete it. The monochromatic emissivity of a series varies as follows, okay? Sorry for lambda less than 0.3 microns, it is 0. It is 0.9 in the range of 0.3 microns and 1 micron. And then again it is 0 for lambda greater than 1 micron. Okay. So what I'm asking you is calculate its emissive power. Emissive power at 1500 Kelvin. These are very standard problems, okay? And this is a selective surface or an engineered surface with vastly different emissivities across wavelengths. So if I have to plot this is EB lambda. And the real surface is not going to be like this, okay? Remember you were saying that the lambda max may be the same. And that's not true for this case. Actually, it is going to be like from till what did you say 0.3 microns. It is 0. So let us say this is 3 microns. It is 0. So I don't have any emissive power. Then 0.3 microns is from 0.3 to 1 micron is 0.9. So let us say this is 1 micron. Now it is going to follow the black body, black surface curve till 1 micron, and it is again 0. So this, my friend, is E lambda. It is not following the shape of the Planck's law. Planck's law is for black surface. Okay. So therefore, this is what I wanted to say through this. I mean, there are surfaces like this. It is possible to make such surfaces. Rest of it is easy. They're asking you to calculate the emissive power, E. And what is E? We know that it is 0 to infinity epsilon lambda EB lambda d lambda. Okay. So what I have to do here is I don't have a same constant value of epsilon, so I have to break it up. I have to say 0 to 0.3 epsilon lambda EB lambda d lambda plus 0.3 to 1 epsilon lambda EB lambda d lambda plus 1 to infinity now this goes to 0, this goes to 0. Okay, so therefore E is equal to 0.9, 0.3 to 1 EB lambda d lambda. And what is that then? This is therefore 0.9 times d 0.3 to 1 sigma T to the power 4. And did I write the temperature? Yeah, at 1500 K. There. Okay, so now we will use our other technique. What will I do? I would say 0.9 d 0 to 1 minus d 0 to 0.3 sigma T to the power 4. Okay, so if you look into the books, the lookup tables, this value till 1 micron, it is not 1 micron. Okay, you have to convert 1 micron times 1500 Kelvin. So lambda T, remember? So this is 1500 and this is 500. So the values come out to 0.01375. And this is very small. Okay. It's like 500, huh? And we found out what? Even for 600, it was almost 0. So this will be 0.00000000001, something like that. So almost 0. And we know this is 5.67 10 to the power minus 8, and this is 1500 to the power 4. So if you do all this, you will finally get the value to be 3553 watt per meter squared. This is your answer. Okay. Let me Now add part B. Find the total hemispherical emissivity, epsilon. Let's do that. Epsilon E lambda by EB lambda. Sorry, E by EB. I'm sorry. So E I have just found out, and EB is sigma t to the power 4. That also actually I have found out while doing these calculations. So it turns out to be 3553 divided by sigma 1500 Kelvin to the power 4. Sorry. Will turn out to be 0.126. Now look at this. If I say that I have a non-black surface with an emissivity of 0.126, okay, would that be a good representation? Okay, certainly not, because 0.126, if I have to plot on this curve, it would go something like this, okay. 0.1, so this here, okay. Even more actually. So this is like E lambda. But look at the characteristics, they're so different. You will emit nothing apart from 0.3 to 1 microns. Whereas a gray body approximation would say that you are going to emit 12.6% of the black body radiation at every wavelength. Okay. So this is an example of an engineered surface where the gray approximation does not work, or will give you very erroneous and incorrect representation of the surface. Okay, questions? Does everybody understand these problems? So friends, instead of, I know as per our curriculum, it's like 310 LTP. Out of the 4 lectures, 1 should be specific for tutorials, but what I think most of the teachers also do, and I do also, is that we, instead of having separate tutorials, sometimes we may have that, but we would put the problems as in between the lectures, okay? So we will have a combination of theory and problems. Okay, so while you are framing your questions, let me give you some idea of what are emissivity values. Okay, so some typical epsilon values. So let us say metals, brass. Okay, so unlike thermal conductivity, which is a bulk property of the material, this is a surface property. So depending on whether the surface is polished or whether it is rough or oxidized, your values are going to be different. Polished surface will have more reflectivity and lower emissivity. Oxidized, higher reflectivity. Similarly, copper, steel, have similar comparable values. Okay. So many a times, for heat sinks, which you are talking about, the finned heat sinks, we do surface treatment. We make the surface rough, especially if you are using it for natural convection. Radiation does play a significant role. You cannot neglect it, even though in our calculations we never considered. I won't say we never considered. We gave you a value, an overall value of heat transfer coefficient. Okay. Now, when heat transfer coefficients are low, then radiation cannot be neglected. Of course, radiation cannot be neglected at high temperatures, definitely, but even at low temperatures, you cannot neglect. If you have a hot surface at 70 degrees and an ambient around at 25 degrees, the amount of heat that you're going to lose by radiation may not be negligible compared to what you lose by natural convection. In fact, they may be comparable. Okay. If you take some non-metals like brick, concrete, paint, cement, this is one. Okay, so they have very high values, like 0.9 or so. They're rough, most of it is absorbed and then radiated. Okay. Your liquid surfaces, and the surface of water in your bucket will have a very high epsilon. Okay, again around 0.9 or so. Now, why I wrote about brick, concrete, paint, cement, etc. Paint, take it with a pinch of salt, most of the paints that we see around. This is because, if you are staying in a ground floor, say a one-story building like the one that I stay in right now, it gets extremely hot in summer. And why ground floor? If you stay at the top floor, okay, of course you will have good airflow and all, but let's say on a still sultry day, hot summer day without any air currents, wind, it gets very hot, right? Because the sunlight falling on the roof is absorbed, okay, and then radiated inside. Okay, so what do we do? You probably have heard this, right? Let me stop sharing now. You have probably heard about heat reflective paints, okay? Even earlier in the olden days, our previous generations, our uncles, fathers and grandfathers, they would say that, you paint the roof with limestone, like chuna, okay? Basically chungkam, I don't know whether it's whether that term is used outside Bengal, but what it means is you make a paint made of limestone and then you just coat the surface of the roof. Okay, why did they say that? Because that is reflective paint. There's something called, what is that? Berger's Nosem, basically snow white paint, and you put it at the top. Okay, these are important because what it happens is, what you're essentially doing is you are increasing the reflectivity of the surface. So instead of having an emissivity of 0.9, if the reflectivity now becomes 0.9, it means the emissivity becomes 0.1. Okay, for a non-transmitting surface, for a non-transparent surface. As we will see later, emissivity and absorptivity are equal. So that's what we try to do. We want to reflect away most of the sun's rays that fall on it. Okay. So very recently, I came across an article. If I find the link again, I will share it with you, either on in Microsoft Teams, you can take a look. Yeah, this is a professor, this is a research group in Purdue University. They are saying, it's a very recent development, probably last week when the press release came out in USA Today, or yeah, in USA, one of the news articles there. What they're claiming is they've come out with what they're calling the whitest surface paint. Now take the whitest, etc. Not literally in terms of the paint color, which may also be white. But here the white means opposite of black. A black surface absorbs everything. A white surface reflects everything. From the thermal radiation point of view, this is white within quotes. So they've come up with this paint where they're claiming that the reflectivity is around 0.98 or 0.99, something like that. And you know, typically when somebody, of course, this is an invention of eminence, extremely noteworthy. But what happens is newspaper reports, of course, they sometimes fluff it up. So they are saying this is going to remove the need for air conditioning and all that. That is probably not true, but definitely it is going to reduce the load of air conditioning, and which is definitely a very significant contribution towards reduction of global warming. Okay, so imagine that if I have this paint on all our roofs, and my AC load goes down by even 50% or even 30%. So imagine the amount of energy savings that we are having. Not just energy savings, the reduction of waste heat being rejected to the ambient, that reduction, right? So indeed, a very significant invention, I would say. I'll try to share that link with you. Okay, so with that, it's 9:59. Thank you very much. Let us end this lecture. I will stop the recording here, and we will meet again tomorrow at 10 a.m. Okay.